and welcome to Project 2.2, the audio reverber. Firstly, the theory behind some of the components. The core component of this audio circuit is the TA2025B amplifier, a dual audio power IC designed to amplify low-level audio signals, making them strong enough to drive speakers. The chip uses a push-pull transistor configuration that improves efficiency and reduces distortion, ensuring clear and powerful audio output. The signal amplification is adjustable based on external components, like resistors and capacitors, allowing for customization of the final audio signal. The LM358 is a dual amplifier IC widely used in electronic applications such as amplifiers and filters. It contains two high-gain operational amplifiers designed to amplify weak signals. The IC is internally frequency compensated, ensuring consistent performance across various frequencies, and is versatile enough to operate with either a single or split power supply, making it suitable for many circuit designs. In filtering applications, it modifies a signal's frequency response, boosting or cutting specific frequencies. The Adafruit Max 9814 microphone is a specialized microphone designed to capture and enhance weak audio signals, particularly useful in systems where signal strength may fluctuate. It features automatic gain control, or AGC, which adjusts the gain based on the incoming signal strength, ensuring consistent volume levels. When the input signal is too quiet, the AGC boosts the gain, and when it's too loud, it reduces the gain to prevent distortion or clipping. In conjunction with this, the bandpass filter isolates a specific frequency range by combining low-pass and high-pass filters. This design ensures that only relevant frequencies pass through, improving audio clarity by reducing noise and distortion. Lastly, 4 to 8K ohm speakers serve as the output transducers converting the amplified electrical signal into sound. Their impedance ensures efficient signal transfer, preventing distortion while producing clear and high-quality audio. Now, the design of the system. The project involves three main circuits. The first circuit handles the initial amplification of the microphone's audio signal. The Max 9814 is used to capture the audio and convert it to an analog signal. Then the LM358 acts as an operational amplifier, or op-amp, that amplifies weak signals, providing gain and conditioning the input signal for further processing. The LM358 output gets sent to the bandpass filter, which isolates the useful frequencies. Then the filtered signal is sent to the Arduino, which produces the reverb effect, and then to the TA2025B amplifier, where it gets further amplified before being outputted to the speakers. One of the key features of this project is the real-time digital reverb effect, achieved through custom code written for the Arduino Nano. The program continuously reads the audio signal input from one of the coupling capacitors after the bandpass filter and processes it with a delay to simulate the reverberation effect. The reverb effect is created by combining the current audio sample with a delayed version of the previous sample. In this code, this is implemented using this line of code, which reads the raw audio input and centers it around 0. The reverb delay is controlled by the reverb delay constant, and the actual delay is managed by comparing the current time with the last reverb time. If enough time has passed, the delayed sample is combined with the current input sample using this line, where last output sample holds the previous audio output, and reverb decay controls how much the delayed sample influences the current output. The code uses an efficient timing mechanism to ensure consistent audio processing at the defined sample rate, 16,000 samples per second, as seen in this line. This ensures that the system samples at regular intervals. Process signal is then output as a pulse width modulation, or PWM signal, to the speaker using this line of code. This line adjusts the processed output sample and writes it to the audio output pin. The result is a real-time reverb effect where the input audio is smoothed and enhanced by the delayed audio, simulating the feeling of sound being played in a larger space. The process of making this project permanent required a custom PCB. To start, create the schematic for the circuit following the prototype on EasyEDA, an online PCB design tool. Once the schematic is complete, convert it to PCB layout and arrange all the components in an efficient way. When done, auto-route the PCB. Then add final touches to the PCB, such as screw holes, your name, the date, and the circuit name. After ensuring all the parts are in place, generate the Gerber file for the PCB and use JLC PCB for fabrication. Once the PCB is completed, create the case. To keep everything safe and professional looking, design a custom case for the system using Fusion 360 and create the case with the same dimension as the PCB for the length and width. Just add 0.4 millimeters so the PCB fits inside. Then download the case file and 3D print it. After receiving the PCB, solder all of the components on the board, put it into the 3D printed case, and secure the PCB with screws through the screw holes. The final result should look something like this.